Hello, myself is Shubham and this is Bitesize Insight. In this video, we introduce the Theorem of Pythagoras, possibly familiar to many of you from school. An application to this theorem is geometrically interpretation of the square root of 2, which we will discuss in this video briefly. So, let's begin. Consider a square of unit length 1. Now the area of this square is 1 square units. Now consider yourself, you are standing in this position and want to move to this point, and then you move towards this point. So if you see, you calculated a distance of 2 units. But is it the shortest distance? No, it is not the shorter distance. The shorter distance will be if I connect these points diagonally. And let's call this distance be x. Now what is x? This is our question. For this, let's pile up these squares like in this arrangement. This large square consists of 4 squares, each of unit length 1. Now, at the midpoint of these lines, connect these all points together. We will form a 2 by 2 square of side length x. Now, if you can see this square consists of 4 right angled triangles, and this is the angle 90 degree with sides 1 and 1 unit. Now if I have to calculate x, suppose I take the area of this triangle. So area of this right angle triangle will be half into base into height, that will be 1 by 2 into 1 into 1, that's equal to 1 by 2. Now this whole square is consist of 4 similar triangles. Now if I need to calculate the area of this complete square, that will be equal to 4 times the area of one specific triangle, that will be equal to 2 square units. And also the area of this square is x square. So from both the equations we can equate that x square is equal to 2. Now I can further state that x is equal to root 2. Now moving forward, what does this actually means? This actually means that now I have a square in which 2 right angle triangles are embedded with side length 1 unit, and the hypotenuse is given by root 2 units. In this you can see the shorter lengths are equal in magnitude, and hence this triangle is also called isosceles triangle. Now isosceles triangle are the triangles with some shorter side lengths equal. Now suppose if I specifically target this triangle and enlarge it. Suppose the given side is A, then the hypotenuse will become root 2a. Now consider C is equal to root 2a. C is equal to root 2a. Squaring both sides, we will get C square is equal to 2a square. That will be C square is equal to a square plus a square. This is the special case of general theorem of Pythagoras. That is special case of general theorem of Pythagoras. Theorem of Pythagoras. And Pythagoras theorem states that if we take any right angle triangle, then the square of hypotenuse is the sum of square of other 2 sides. This is basically the theorem of Pythagoras. Let us understand what this actually means in another sheet. So as I said, the theorem of Pythagoras states that the square of the square of hypotenuse, that is c, is c square is equal to the square of other two sides in a right angle triangle, that is a square plus b square, implies c is equal to under the root a square plus b square. This specific expression c is equal to under the root a square plus b square is also known as surd, which we will discuss further in our further videos. Now you don't expect it to simplify, but occasionally it will. For example, surd generally doesn't simplify as easily, but if we take some general example, for suppose if I take a is equal to 3 meter and b is equal to 4 meter, then c square will be 3 square plus 4 square, that is 9 plus 16 is equal to 25. C square comes out to be 25, implies c is equal to 5 meter. This simplify easily. Now let's discuss what does that actually means. Now that the example of surd we have taken simplified easily, usually surd expression don't. If we go back to the unit square, the hypotenuse has length root 2 that can be expressed as fraction. Now of course the length, the distance between 2 points is very important, and ancient mathematics wanted mathematics to be sufficiently powerful to model distances between points. Hence studying root 2 was a very powerful mathematical entity. For example, we started with counting numbers and then fractions of counting numbers called rational numbers, and it was an important question whether the mathematics of fraction was sufficiently powerful to model distances like root 2, and it turned out the answer is no. Root 2 is not a fraction. Again, I'm going to try and explain why this is the case. Suppose root 2 is a fraction. What does that implies? Root 2 can be written in the form of a upon b, where such that a and b have no common divisors. What does this statement signifies? This signifies that a and b are counting numbers, and we have cancelled off any common divisor in the numerator and denominator, and this is in reduced form, implies nothing is common between them. So taking this equation and squaring both sides, we will get 2 is equal to a upon b square, implies a square upon b square, which further implies 2b square implies e square. From this statement we can say that a is an even number. Say a equals to 2c. Now substitute back a in this above equation, we will get 2b square is equal to 2c square, that is equal to 4c square, which further implies b square is equal to 2c square. Hence we can also say that b is also even. Now consider these two statements which I am highlighting, this and this. We are saying that b and a both are even numbers, but it contradicts our above statement that says that a, b have no common divisors. But in this case we see as a is also even, b is also even, both are having same common divisor, that is 2. Hence root 2 is not a fraction because it contradicts our above statement. Hence we can say that our knowledge of rational numbers and counting numbers was not sufficient to deal with the quantities like root 2, root 3, root 4 and so on. Hence, in order to simplify our mathematics further, we introduced the concept of irrational numbers, which further contributed to the concept of real numbers. I hope this will be sufficient for you to grasp the knowledge and work on it. Work on some examples and you may find it well worthy enough, and I think this should be enough for today and we should sign off now. Okay.